Hi, everyone. I'm Negar Mehr. I'm a postdoctoral scholar at Stanford University, working with Professor Max Schwager in the Multi-Robot Systems Lab. And I'm very excited to be part of this workshop to talk about some of the recent work that has been done at MSL on enabling safe robotic interactions in the presence of uncertainties. So we're living at a very exciting time when everybody is expecting robotic systems to enter our daily lives and operate in real world. In all of these real world applications of robotics that we are envisioning, robots need to interact with other agents surrounding them. For instance, drone delivery systems or other type of robotic delivery systems need to interact with humans in an environment. An autonomous car may need to interact with other humans or potentially other autonomous cars on road. So one critical aspect of all these real-world applications of robotic systems is that robotic systems need to maintain safe interactions in all these examples. So you don't want your drone to collide with you when you're running, or you don't want an autonomous car to get too close to a human or even collide with a potentially another autonomous car on road. So it's an important aspect of the task for the robots to maintain these safe interactions with the agents around them. But this in general can be very challenging in the real world because uncertainties are an inseparable component of robotic systems, as well as the environment that they are operating at. So robotic systems are subject to noise, and they are fundamentally stochastic dynamical systems. And they're also expected to operate in a world which is shared by other agents whose motion could also be uncertain and stochastic. As a result of these underlying uncertainties, when planning for their actions, robots need to account for the underlying risks or the risks that are associated with taking certain actions. But accounting for the risks that are associated with the underlying uncertainties is not enough. An autonomous car could trivially avoid all the risks by not moving at all. The challenging aspect of planning in the presence of uncertainties is that you want the robot to account for the underlying risks in an efficient manner. So you expect your robot to operate a task as efficiently as possible while maintaining safety. So how to address this trade-off is actually a very challenging problem. And throughout this talk, I'm going to talk about how risk-sensitive control could actually be a promising framework for enabling safe and efficient robotic interactions in for real-world applications of robotic systems. So first, I'm going to discuss how risk-sensitive control can be utilized in planning safe robotic trajectories. And then I will talk about risk sensitivity in interaction. I will talk about the behaviors that emerge from the interaction of multiple risk-sensitive agents. So to convince you why risk-sensitive control could potentially yield to safe behaviors of robotic systems, let's just focus on the first part, which is really giving an introduction of what is risk-sensitive control. And to discuss the framework of risk-sensitive control, let's examine a crowd robot navigation scenario. So imagine that a robot wants to go from a start position to a goal, but the scene and the environment is shared by a couple of humans. So a robot wants to go to its goal, but at the same time, it wants to make sure that it doesn't collide with the humans that are in the scene. The human motion, for such an example, is inherently stochastic and uncertain. So the robot can view this joint human-robot system as the robot itself being one agent that needs to plan, and the humans around it, which are sources of uncertainties that the robot needs to deal with, and view this human-robot system as a joint stochastic system where the human motion actually contributes to the underlying uncertainties that the robot needs to deal with. So if you view this human-robot system as a joint stochastic system, let's see what we could achieve by classical planning under uncertainty approaches. So assume that the dynamics of this joint stochastic system can be represented potentially as a nonlinear dynamical system, which is subject to uncertainties. In the classical risk-neutral planning, the robot optimizes for its actions such that the expected cost of its trajectories is minimized, where the cost function J can include different aspects of the task that are relevant for the engineer. For instance, the cost function J could be designed such that it penalizes for collisions, it penalizes the tracking cost or the control cost, etc., whatever thing is really important for successfully achieving the task. But if the robot uses such a risk-neutral planning framework for this crowd robot navigation example, here is the type of behavior that you would get if the robot uses a risk-neutral planning in the presence of uncertainties. On the left, you can see that the robot gets very close to the human, and it is finally the human who actually bypasses the robot and just clears the scene. But the robot is clearly in this confusion mode with the human's motion around it. This is clearly not a safe behavior to observe from a robot. So let's just see how we could achieve safer trajectories for the robot by reasoning about these uncertainties that are inherent of humans' motion. So going back to our joint stochastic system, I'm going to show that we can avoid such confusion modes and unsafe behaviors by using the framework of risk-sensitive control. So now, assume that the robot is actually reasoning about the underlying risks. And going back to the setup that we have the dynamical system representation available, this time assume that the robot is using an entropic risk measure and optimizes an entropic risk measure of its cost function J, where the entropic risk measure is defined as the log of the expected exponential of the cost function. This is a standard risk measure that has been well studied in control theory and controls literature, which includes also a tuning parameter theta that adjusts the sensitivity to the underlying uncertainties to see how this modified objective function actually leads to a more risk-sensitive or potentially risk-seeking behaviors. Note that this entropic risk is approximately equal to the expected cost of the planning plus theta times the variance of the cost function. This shows that if we set theta to be equal to 0, we recover the classic risk-neutral setting, which is just minimizing the expectation of the cost function. Of course, this holds in the limit, but just intuitively. While if we let theta to be something greater than 0, then a trade-off between expected cost and the variance of the cost function could actually be minimized. So this means that when theta is greater than 0, then we are minimizing for both the expected cost and the variance of the cost. So effectively, we are reducing the variance, although it may lead to larger expected value of the cost. On the other side of this spectrum, if you let theta to be less than or equal to 0, then higher variances are favored, and therefore the robot would have a risk-seeking behavior. Entropic risk measure is a well-studied risk metric, and as I said in controls literature, because first of all, you have a knob for tuning the level of sensitivity to the risk through this parameter theta. And more important, entropic risk provides a computationally tractable metric for reasoning about the underlying risks. So it enables and it provides a computationally tractable metric for reasoning about the underlying uncertainties. Now, again, for our crowd robot navigation example, if the robot plans its trajectory using this time a risk-sensitive control rather than a risk-neutral control, then it should minimize the entropic risk measure, which is, as I defined, the log of the expected exponential of the cost function. But to compute this objective, the robots need to be aware of the underlying probability distribution of the uncertainties, which in this case is a probability distribution of human motion. But how can we get this? We need this to be able to minimize this objective function. To get this probability distribution, we use a Trajectron++, which is a trajectory forecasting framework developed in Autonomous Systems Laboratory at Stanford. Using Trajectron++, we could model this underlying distribution of human motion. And here is the type of behaviors that we got by using a risk-sensitive controller in conjunction with Trajectron++. On the left, you can see the robot's navigation example where the robot is risk neutral. And on the right, you see a risk-sensitive robot. You can see that the risk-sensitive robot is actually more likely to yield to the other agents in the scene, and risk-sensitive lets the other agent pass first, and then it moves forward. The same behavior could actually be observed when there are multiple agents or multiple humans around the robot. Again, a risk-sensitive robot yields to the humans and let them pass, and then moves forward. It somehow reasons about the fact that human motion is uncertain, so let's take a safer action, which is yielding to the humans and let them pass first. Amazon researchers actually conducted a real-world experiment with one robot and 5 humans around to see if we could avoid those confusion modes of the robot in our real-world experiments using the framework of risk-sensitive control. And here is the type of behavior that we got from the robot in this real-world experiment. The risk-sensitive robot could actually successfully navigate in the environment without getting too close to any human and creating those confusion modes for both for the humans and the robot. All right, so this is one example of how risk-sensitive control could actually allow for safe trajectory planning in the presence of uncertainties. But so far, the robot has been the only risk-sensitive agent in the environment. We didn't assume anything about humans being risk-sensitive or risk-sensitive. But now let's see what happens if there are multiple risk-sensitive agents in the environment. Let's see what behaviors will emerge from the interaction of multiple risk-aware agents. So now in this example that we had, let's replace these human agents by some other risk-sensitive agents. Let's consider the scenario where there are multiple risk-aware agents that are interacting with each other. How can we study this? And how can we study the type of behaviors that will emerge from this type of interaction? In general, interactions, it is well known that interactions could actually be best represented via dynamic games. So in this case, it is natural to think about interaction of risk-sensitive agents by studying the behaviors that will emerge from studying risk-sensitive dynamic games. So what we do to study these emerging behaviors is to model the joint system via the framework of risk-sensitive dynamic games. In particular, we are assuming that every agent is optimizing an entropic risk, and we want to see what type of behaviors would emerge as we vary the risk sensitivity of each agent. So assume that the dynamics of the system is again some potentially nonlinear dynamical system which is subject to uncertainties, and having access to the dynamics of this joint stochastic system, assume that every agent optimizes an entropic risk measure. with its own level of risk tolerance. So one agent could be risk-seeking, the other one could be risk-sensitive, one agent could be risk-neutral. Every agent could have its own level of sensitivity to the underlying risks. Then, if we consider a game between such agents, the outcome of such an interaction or such a game is obtained by finding the state feedback policies that are Nash equilibrium policies for this risk-sensitive dynamic game. So to study what type of behaviors will emerge from this interaction, we need to be able to compute the Nash equilibrium policies of risk-sensitive dynamic games. But how can we compute Nash equilibrium policies of risk-sensitive dynamic games? Computing Nash equilibrium solutions is very challenging even for deterministic dynamic games. So you could imagine that it is non-trivial to actually find this Nash equilibrium policies for risk-sensitive dynamic games. So what we did was we tried to actually approximate the Nash equilibrium solution of such games via one result that we leveraged actually for our approximation. So one of our findings was that if we have a linear dynamical system, and we assume that every agent is optimizing an entropic risk of a quadratic objective function, a convex quadratic objective function or cost function of its state and actions, then we've shown that the Nash equilibrium policies of such a linear exponential quadratic game can be obtained in closed form, actually, by solving a modified version of Riccati equations. So this was a great result because now we know we can compute the Nash equilibrium policies for this class of risk-sensitive dynamic games in closed form. And we leveraged this result for approximating the Nash equilibrium policies of general risk-sensitive dynamic games, where for general systems, we can iteratively linearize the dynamics, obtain a quadratic approximation of the cost function, and find the Nash equilibrium policies for the approximated LEQ gain, and forward simulate the system and repeat this process until convergence. So this iterative algorithm provides a mechanism for approximating the Nash equilibrium policies of risk-sensitive dynamic games. All right, so now that we have an algorithm for studying the interaction of risk-sensitive agents, let's see what type of behaviors will emerge if we use this algorithm to study the interaction of risk-sensitive agents. On the top row, you could see the equilibrium policies and strategies for an intersection and merging scenario when the green agent is more risk-averse, whereas on the bottom, you could see the outcome of the interaction with the red agent is actually more risk-sensitive. As you can see, again, the agent which is more risk-sensitive yields to the other agent, which is expected and an intuitive behavior. If one agent is more risk-sensitive than the other, then it is yielding to the other agent. But how is this different from the experiment that I showed in the first part of the talk? What actually have we gained by what we have gained? What did we gain by including both risk sensitivity and capturing the interaction? And to answer that, I'm going to first show you what we gained by including risk sensitivity in the interaction, and then show you what we gained by including interaction and not treating the agents as decoupled agents in the scene. So first, let's compare the outcome of the interaction for two cases, when the agents are risk neutral and when the agents are risk sensitive. What we have done is that we've plotted the minimum distance between the two agents during their interaction for, again, both the intersection and merging scenario as a function of the level of noise and uncertainties in the system. And as you can see with the increase in the level of uncertainty, the minimum distance between risk-sensitive agents increases, while the risk-neutral agents do not really react to the underlying noises and to the underlying level of noise. This is also intuitive because if the two interactive agents are aware of the underlying uncertainties and they are aware of the fact that the level of uncertainty is high, they would maintain a larger distance from each other and they would rather not get too close to each other because the level of uncertainty is high. So intuitively, the higher the uncertainty level gets, the more conservative the agents act to sort of maintain, to make sure that they maintain their safety. So this sort of shows that risk-sensitive agents actually react to the different levels of noise or uncertainty in the system, despite the risk-neutral interactive agents. But now that we've got the answer to the first question of like, what did we gain by including risk sensitivity? Let's see what we have gained by including the interaction of risk-sensitive agents. What would have happened if we just looked at decoupled risk-sensitive agents that treat each other as some moving obstacle? So again, for our intersection and merging scenario, for a fixed value of risk sensitivity of agent 1, we have plotted that the time that it takes to pass for different values of theta 2, or the risk sensitivity of the second agent, in these two scenarios. And we studied two cases for each environment. Interactive agents, the time that it takes to pass for the interactive agents versus the time that it takes to pass if the agents were treating each other as moving obstacles and they were not taking into account that they can affect the actions of the other agents. So you can see that the reasoning about interaction actually leads to better efficiency of the agents and reduces the time that is required to pass. The gain that agents are getting in efficiency will probably become more clear and more obvious in a roundabout scenario that we have simulated in Carla environments. As you can see, the time that it takes to pass is significantly smaller when the agents reason about their interactions and they are aware of the fact that they are interacting with each other and they're not just two decoupled agents. So this sort of shows that risk-sensitive agents actually achieve higher efficiency. Interactive risk-sensitive agents achieve higher efficiency while they are maintaining safety. So this sort of answers the two questions that I raised about what do we gain by capturing risk sensitivity in interaction. But let's look at the outcome of the interaction of two risk-sensitive agents for different pairs of risk sensitivity parameters. So again, for our intersection and merging scenario, we changed theta 1 and theta 2, which are the risk sensitivity parameters of agent 1 and 2. For each pair of risk sensitivity parameters, we generated 100 simulations of the system and plotted the frequency of the green agent yielding to the red agent for various pairs of risk sensitivities. And here is the heat map of the frequency of yielding. You can see that if you look at every row, as the risk sensitivity value of one agent increases, the frequency of that agent yielding to the other one actually increases, which is again intuitive behavior. But more interestingly, in these heat maps, if you consider the diagonal elements of the heat map, which are actually the cases where the risk sensitivity of the two agents are equal, then you can see that the frequency of one agent yielding to the other is roughly 50-50, which is again an intuitive behavior, because if the agents are treating risks equally, then like 50% of the time one would yield to the other one. Another interesting observation is that for the parameters for the risk sensitivity parameters that have the same difference, which are actually the risk sensitivity parameters that are, or the elements of the heat map, which are parallel to the diagonal, the yielding frequencies are roughly similar. So if you look at the lines for which theta 2 minus theta 1 is like a constant, most of the times quality of the interaction is the same for those pairs of risk sensitivity. But let's take a look at another metric. Let's take a look at the heat map of the minimum distance between the players for different pairs of risk sensitivities, theta 1 and theta 2. For the minimum distance, you can see that the plots are very symmetric with respect to the diagonal. This means that if, for instance, theta 1 is equal to 1, theta 2 is equal to 0, the minimum distance between the two agents is the same as the case where theta 2 is equal to 1 and theta 1 is equal to 0, which is, again, an intuitive behavior, right? But even in addition to that, as you get further from the diagonal elements, which are the scenarios for which theta 1 is roughly the same as theta 2, and by getting further from the diagonal, I mean as the relative risk sensitivity between the agents increases, the minimum distance between the two agents increases as well. So the higher the minimum the relative risk sensitivity between the two agents is, the higher their minimum distance would get in a symmetric way, actually. So these empirical observations are somehow telling us that when it comes to interaction of risk-sensitive agents, it is the relative risk sensitivity of the agents that determines the outcome of the interaction rather than the absolute risk sensitivity of every agent. What does this mean intuitively? So imagine that you're sitting in an autonomous car, which is inherently a risk-neutral agent. But when this car is interacting with another car which is too risk-sensitive, then your autonomous car may exhibit a behavior such as overtaking, which can be interpreted as a risky maneuver in itself, while your car is in fact not like a risk-seeking agent. So this shows that dependent on the difference between the agent's sensitivity to the underlying risks, the outcome of the interaction could vary. And the outcome of the interaction is not a function of the absolute risk sensitivity of one agent or the other. It depends on the relative risk sensitivity between the two and how every agent is going to leverage and exploit that difference for better efficiency of itself. So in summary, what we have found so far is that risk-sensitive control as a computationally tractable framework for ensuring safe and efficient robotic interactions in the presence of uncertainties. Both I showed you through the first part of the talk that it could lead to safe navigation of robots. And then in the second part of the talk, I just showed that how reasoning about interactions of agents that are aware of the underlying uncertainties could lead to further efficiency of these safe interactions of robotic systems. If you're interested in reading more about the details of each one of these works, you can refer to two of our recently accepted IRS papers by multi-robot system lab members. And with that, I would like to thank everyone who has contributed to this line of work, from Multi-Robot Systems Laboratory, Autonomous Systems Laboratory at Stanford, and Toyota Research Institute. So if you have any questions about either of these works, feel free to reach out to me. Right now, I'm a postdoctoral scholar at Stanford, but I will be starting as an assistant professor at University of Illinois, Urbana-Champaign next fall, and would be happy to chat. Thank you for listening.